what they want. Nowhere in this question did it say the word oxidation number, did it? You just had to know that you had to use it. So, again, getting that logic down is very important. Now, for the titration at the equivalence point, calculate the number of moles of each of the following that is reactive. So they want to know moles of permanganate. That one's easy, isn't it? Because they tell us in the question that we've got 0.0150 molar, so there's a molarity, and they're telling us that it uses 17.8 milliliters, so there's a volume. So I can use molarity times liters equals moles. Now, in the problem, they're telling us that's potassium permanganate. In the question, they're asking for permanganate only. They don't say that the potassium's in there. But when you look at that compound, there's one permanganate ion in one formula unit of potassium permanganate, right? So if it's 1 to 1, it's the same. Be careful. They may ask you something that's not 1 to 1. Now, they may give you one that's got 2 of something, and you have to figure out the molarity or the moles. So I have 0.0150 molar, and they don't give me liters, but they do give me 17.80 milliliters. And I'm sure 99% of you know what to do here, but when you're calculating liters from milliliters, you just move 3 decimal places, right? Well, in every class, I'll have a student or two that can't remember which way to move the darn thing. Let me show you a little trick. Which of these units is bigger and which is smaller? Milliliter or liter? Liter's big, milliliter's tiny, right? So, the big number goes with the small unit. The little number goes with the big unit. Does that make sense? Big number, little unit, little number, big unit. If you remember that, you'll never make a mistake if you move it the wrong way. Okay, so got our molarity multiplied times our volume in liters, and we come out with 2.67 times 10 to the minus 4 moles. Pretty easy question there. The second part says, what's the number of moles of oxalate ion? Well, if you start looking back in the problem, they don't give you any measurements of oxalate at all, do they? So again, they're sneaking a concept question in here. They're seeing if you know what the equivalence point means, what a titration is. When you do a titration, you've got your substance in the flask, you're adding another substance from a burette, you've probably got an indicator in there that's going to change color. This one's actually a self-change color because permanganate goes from purple to brown. So you can actually figure out how much oxalate you have from the permanganate. Now, I hear students say, well, the moles have to be equal at the equivalence point. That's not necessarily true because I have 2 permanganates and 5 oxalates, so that their moles are definitely not going to be equal. But I can figure it out using stoichiometry. So if I have 2.67 times 10 to the minus 4 moles of permanganate ion, I look at my balanced equation. 2 moles of permanganate ion require 5 moles of oxalate ion. My moles cancel. So 2.67 times 10 to the minus 4 times 5 basically divided by 2. I get 6.68 times 10 to the minus 4. into the wrinkle that we often see on the AP questions. Part 3 says, calculate the total moles of oxalate that were present in the 100 milliliters of prepared solution. Now remember, back up in the question, it said that we took this 100 milliliter solution, we took 20 milliliters of it, titrated it. So we have a bunch over here we didn't use. Well, instead of actually titrating the whole 100 mils, we're going to titrate 20 milliliters and then just do a calculation. So that's 6.68 times 10 to the minus 4 moles of oxalate. That's per 20 milliliters of solution, right? Anytime you see the word per, that means divided by. So it's that much per 20 mils of solution. And I want to know how much is in 100 milliliters of solution. So this times 100 divided by 20. Since this number times 5. And what do I get there? 3.34 times 10 to the minus 3. Also in that first step, it said that this is an impure sample. Now they want to know what's the percent of beryllium oxalate in that impure sample that we started with. Well, I know how many moles of oxalate I've got, and when you look at the formula for beryllium oxalate, for every one of these, I get one of these, don't I? So if I have this many moles of oxalate, I should have the same number of moles of that since it's 1 to 1. Now to get a weight percent, I need mass, don't I? So how am I going to convert this moles to mass? Formula 8. What was the formula 8? 151. 151.1. Got it backwards, didn't I? I left a multiplier out here, by the way. That's 3.34 times 10 to the minus 3. Now notice, 10 minutes, okay. Notice I made a mistake there and I immediately recognized it because I had it set up in dimensional analysis formula. This moles cancels that moles out. If you write it out in dimensional analysis form instead of just using formulas, grams per mole, that sort of thing, you'll catch mistakes that you wouldn't have caused otherwise. So when I calculate this out, I get some number. Oh, there it is, 0.324 grams. So that's how much beryllium oxalate I had. My original sample of beryllium oxalate was 0.345 grams, so there's not much impurity in there. So to get my percent beryllium oxalate in that sample. You got a different answer?
I got 25.
I can't hear too many. What did I miss?
0.5047.
Oh. You know why? What's this weighed up? That's the hydrate. So don't trust your memory. Yeah, it is supposed to be 97 point. My bad. Is it 97.1? 97.0? Now did you get 0.324?
Yes.
So we're back on track? Okay. So, my percent BEC204 is going to be equal to mass BEC204 divided by mass of sample times 100. So I've got 0.324 grams divided by 0.345 grams of sample times 100. And I end up with 93.9%. You guys are going to experience the same type of thing on the test. You're going to be in a hurry. You make mistakes. Practice, practice, practice.
Almost fixing to go to break. I think it's like probably like 5 minutes.
Okay. We only have a few minutes left, so very quickly, let's talk about a couple other things. One of the problems that you're going to see, probably more than one, probably several of the problems you're going to see, and even multiple choice, is limiting reagent. In other words, what do you run out of first? There's all kinds of ways that you can do limiting reagent, and a lot of people will actually do the calculation with one starting material, work it all the way through. Then they'll come back and do the same calculation with the other starting material, work it all the way through, and then they take the one that's the smallest. So there you spend probably 10 or 15 minutes working a problem that really would have only taken 7 minutes. Well, that really kind of hurts you on the overall exam because you may not finish. So anytime you see a limiting reagent problem, I'm going to give you a little shortcut. The little shortcut is, first thing you do is you convert your reagents to moles. So if I've got 2 reagents, convert them both to moles. If I got 3, convert all 3 of them to moles. Then divide each each number of moles by its coefficient from the balanced equation. And the one that you get tells you what your limiting reagent is. Now that number that you get, this result, don't start with that number on anything. Once you figure out which one is your limiting reagent, circle it, say this is my limiting reagent, all calculations begin with this, but do not use that number for anything. Okay? That's just a quick little method that'll help you with limiting reagent problems. And you're going to get, like I say, multiple choice is going to have a bunch of these. I'm going to, now let's go ahead and take a look at this one here. Feel free to take pictures with your iPhone. We are very short on time, we have to go pretty fast. We've got a sample here that's solid, and we're going to add it to a solution. And it says there's no change in volume. That makes our calculations easy. The chemical reaction that takes place is this. You're going from lead nitrate solid plus sodium iodide to lead iodide plus sodium nitrate. So this is a double replacement reaction where you have it precipitate. This is an observation that provides evidence that a chemical reaction took place. Well, and sometimes you can just say, hey, I mixed two solutions in a solid. That's evidence. Or a gas form, or heat was given off, or there's all kinds of evidence. But if I mix a solid and a liquid and I get a solid and a liquid, what are you going to say? Sometimes they ask you questions to see if you've done these experiments in lab. Because if you actually saw this experiment in lab, you would easily remember it because it goes from a colorless, two colorless things being mixed together to yellow. So that color change is a pretty good indication. So you have to not only say look for a precipitate, but you have to look for the colors and other physical appearance to see the reaction. We take our sample, mix them together, calculate the number of moles in each. Well, for the lead nitrate, we actually are given a mass, so we can just use our formula weight and get our moles of lead nitrate easy enough. But for sodium iodide, they don't give us a mass. They give us a volume.